Hey there, it's Shannon Math Chick Myers, and today we'll talk about some Boolean algebra. So so far we've learned about logical equivalences using, the P's and Q's and the notation that goes along with that, or statement variables, P, Q, and R. And we've also used set properties, so for all sets A, B, and C. So I'm not going to read through all of these things because you'll get very bored and probably fall asleep. But I'll scroll through slowly just in case you don't have the handout. And what we'll be looking at today is some different notation. It's really a lot of the same stuff that we went over, especially in 6.3 when we were proving statements about sets algebraically. But we'll be using the notation for Boolean algebras. So here we go. And we'll get right on with our definition. So in Boolean algebra, the dot like this is like is like the intersection. The plus is like a union. 0 is contradiction. One is a tautology. And then if you have a line over, if you have a line over the A, that's kind of like, would be in set notation, kind of like an A complement, not A. Okay, so anyway, that's what we'll be doing. So a Boolean algebra is a set B together with two operations, generally denoted with the plus symbol and this dot here like a times symbol, but it means intersection, such that for all A and B and both A or B and A and B are in B, and the following properties hold. So commutativity holds. I'm going to go through these pretty quickly because you've seen all of these in the other formats. So now it's just getting used to them here. So A or B equals B or A. So just get used to saying it like that. And the second one would be A and B equals B and A. That's our commutativity laws. So associative laws for all A, B, and C in B for Boolean. If you've got the quantity A or B or C, that's equivalent to A or B or C. And if you have the quantity A and B and C, that's equal to A and B, the quantity B and C. So distributive laws. These are going to look a little strange, but it's all right. So if you've got A or B and C, that's equivalent to A or B and A or C. And then if you've got A and B or C, that's equivalent to A and B or A and C. We also have identity laws. So if you have A or 0, which remember stands for a contradiction, right? That ends up equaling A. If you've got A and 1, that's going to equal to A. So for complement laws, what we have for each A and B, there exists an element B denoted like this and called the complement or the negation of A such that A or not A is going to equal to your tautology. And then if you have A and not A, that would of course equal to your contradiction, which is denoted with 0. Okay? All right, so let's get to this theorem that has several properties of a Boolean algebra. So B is any Boolean algebra. 1, uniqueness of the complement law for all A and X in B if A or X is equal to a tautology and A and X is equal to a contradiction, then X is equal to not A. Okay? Uniqueness of 0 and 1. So if there exists an X and B such that A or X is A for all A and B, then X is 0. And if there exists a Y and B such that A and Y is equal to A for all A and B, then the Y is going to be 1. Double complement law. So for all A that belongs to B, if you've got a not A, those are parentheses there, not A is equal to A. Idempotent laws. So for all A and B, if you have A or A, that's equal to A. And if you have A and A, that's also equal to A. Those are very useful. Universal bound laws for all A and B. If you have A or 1, you're going to get 1. If you've got A and 0, you're going to get 0. And remember, 1's like a tautology, 0's like a contradiction. I guess you could also, in set notation, you could think of it as universal set would be like your 1, and empty set would be like your 0, or null set. De Morgan's laws. So for De Morgan's laws, if we have not A plus B, that's going to equal to not, and actually it's not quantity A or B. That's better to say it like that. And that's going to equal to not A and not B. And if you've got not A and B, then that one's going to be not A or not B. Absorption laws for all, again, very useful for all A and B that belong to the Boolean algebra B. First one we have would be A or B and A is equal to A. A and B or A is equal to A. Complements, so if you have not 0, you're going to have 1. If you have not 1, you're going to have 0. Cool, cool? All right, so here's a few examples. The first example, we're assuming B is a Boolean algebra with the operations or and define, the plus and the dot. Prove each statement without using any parts of the theorem unless they've already been proved. You may use any part of the definition of a Boolean algebra and the results of previous exercises. Okay, so here we go. For all A and B, A or 1 is equal to 1. So here we go. For our proof, we're going to let A be any element of this Boolean algebra, B. So for our left-hand side, we have A or 1, right? Well, what is 1 equal to? Do you remember? There's a few things. And remember what we want to get to 1 on the other side. So I'm kind of thinking complements might be good. So if we replace this 1 with, so the A or is from the first two things here. And then in place of the 1, I'm going to put A or not A. So these guys are equivalent. And so putting down our rules we're using, these are from our, not properties, but from definition. Okay, so we're going to use the complement laws. All right, so alrighty, and next up, that's going to be equal to, what are we allowed to use? Beautiful. Associative law, I think, would be pretty useful. And then if you have A or A, what do you get? Beautiful. A. So this here, A or A was A. And then we'll have plus not A. And that was what? Good. That was from the idempotent laws. And then A or not A is 1. And that was from complement. So we used all definitions here. Complement laws. And so A or not A was 1. Cool, cool? All right. Very good. So next one, for all A and B, quantity A or B and A is equal to A. So again, we start our proof by identifying everything. And if we say for all elements A and B in B in B, what's going to happen? Our left-hand side will be, so we have the quantity A or B and A. So what is that equal to? Well, we don't quite have something there. We don't have a distributive that way, but can't we commute them? And then we can apply the distributive law in the next step. So this one was commutative laws. And then this will equal to A and A or A and B. That's by our distributive laws. And then we have this one will equal to, well, A and A, it's just A by the idempotent laws, right? So we'll have A or A and B. And then now let's see what we're going to have. This one we're going to use a little bit of a trick. So remember that A was also equivalent with A and 1. So we're gonna apply that. A and 1 is the same as A, and we still have A and B, that quantity. And this is from the identity laws. And now we can use the distributive laws backwards, right? So this one will get A and 1 or B, right? And then next up, what will we have? Well, if we commute the 1 and the B, I think that'll be useful. Or it's the commuting the B and the 1, that the sign is the or statement. Alrighty, and remember that if you've got B or 1, you just get what? 1. Good. So that'll be A and 1. And that's from this one. And that property is called a universal bound law. And then we're almost done. We'll have A and 1 is equal to A, and that one's by identity laws. And that, of course, is equal to our right-hand side. And we're done with that problem. Cool, cool? Awesome. All right, and then the third example, we have for all A and B, A and B or A is equal to A. So let's do it. So our proof for all elements A and B in the Boolean algebra B. So for our left-hand side, we have A and B or A is equal to. So what do you think we should do? It's again using that one trick, right? It's the A and B staying the same, or A and 1. So the A and the A and 1 are equivalent. And that property is just the identity law, or one of the identity laws. Okay, so then next up we have this one. Remember that trick? You can factor out the A, or use the distributive law backwards. Really, it's not quite, we won't call it factoring here. And so then we'll have A and B or 1. That was from the distributive laws. And then B or 1 is good, 1. So then you'll have A and 1. And that one was from our that universal bound law. And then we will get this one will equal to A, and that's by identity laws. And that is equal to our right-hand side, and we're all done. Fun times, huh? All right. So now the last problem we're going to do today is a little bit more complicated, but not awful. For all A and B, not A plus B is equal to not A, well, we won't do the pluses. Not A or B is equal to not A and not B. So let's check it out. So for all A and B and B. So what we're going to do here is there's two things that we need to do. We need to show that, so we'll do it in parts. So part one, we want to show that A or B and not A and not B is equal to 0. Okay, so let's do this. So the left-hand side of part one is A or B and not A and not B. And that in turn is equal to, let's start with commuting these, because I think what'll happen is it'll be easier when we use the distributive property if we first commute these two. So commuting them, we'll have not A and not B, that quantity, and A or B. By the commutative laws. And then we will have, using distributive laws, if we take not A and not B and A, and then or not A and not B and B, believe it or not, it'll do something good for us. So those are distributive laws. And then next up, what will we have? Good, we will have, by using the commutative laws, right, because they have all the same operator inside the parentheses, so we're going to have not A and not B, or not A and not B and B. And those were by associative laws. Let me make sure I didn't use anything else. And commutative laws. And then next up we will have, so not A and A was equal to what? Good, 0 and not B. And then over here we'll have or not A and 0. And then we will have what? Beautiful. 0 or 0, which is 0. Now, the next part that we want to do is we want to show that quantity A or B, or not A and not B, is 1. And once we've shown both of these things, we will have completed the proof. Okay, so let's do it. Left-hand side, A or B, or not A and not B, equals. So for this one, let's go ahead and, do you see that by distributing this, it'll be easy to use that associative property after. It's already set up for it because we'll have all pluses in each set of parentheses with an and or a dot in between. So I'm going to go ahead and do it right away. So we'll have A or B, or not A, and A or B, or not B. And that was, oh, I forgot to fill in some of those things. Sorry, above. This one here were the, this first one was complement laws. And then universal bound laws. And then this would have been the idempotent. Okay. All right, so next up, we'll continue with what we were doing here. Sorry. So now this in turn will be equal to, if I commute some terms, I'll have A or not A, or B, and A or B or not B. So on the, I use the commutative and the associative laws. On that one, and then we will have, so A or not A is equal to what? Beautiful. 1, and then we'll have our or B. And then what will we have? Dot A or, and then B or not B would be 1. And those were by complement laws. And then I really should have probably commuted a term up here. I probably should have done another step saying, you know, not B and 0 before I went, you know, down 1, but sorry about that. All right, so here we go. Now this one I will do so. So if I commute this one, we'll have B or 1, and this is 1, right? The A or 1 is by, the first part was the commutativity, the switching the B and the 1. So commutative and universal bound laws. And so this here was the universal bound part. And now we'll use the universal bound for this part here. B or 1 is going to be 1. And then we'll have 1 and 1. So that was from the universal bound laws again. And lastly, 1 and 1 is 1. And that is because why? Idempotent laws. And that was our right-hand side. We're going to come back here and check out the uniqueness of the complement law. Okay, this is why we did all this. So we did it kind of the other way, right? Ours were switched around, right? So here, well, our conclusion will be by the uniqueness of the complement law, these things will be equivalent, okay? And remember, our initial was that not A or B is equal to not A and not B. Okay, so that's all we have for today. I hope you enjoyed the show, and I hope you have a wonderful morning, afternoon, or evening whenever you are watching. And if you like what I'm doing, please subscribe and tell your friends. Bye.